Hi, I'm Miss Hall,
Hi, I'm Mr. Sajak.
and this is lesson 44, the natural base e. Okay, so for the first time, we're learning about the natural base e. And e is irrational and is defined as follows.
Okay, so E is like the number pi, and that's what we're saying when it's irrational here.
Right. Okay. And there's a button on your calculator that's e.
Yeah.
And e is approximately 2.718. You're always just going to use your calculator e.
I think it's on the divide symbol for most of your TI 83s and 84.
I left my calculator at school. We'll look at it at school. So this is the idea. Instead of, it kind of travels from, we've just been doing compound interest, about compounded quarterly, monthly, daily, and now it's just compounded continuously. It just grows and grows and grows. Right?
Mm-hmm.
And that brings us to a base amount of E, which is 2.718, blah, blah, blah. Any more I should say about E?
If you're interested, if you think this is a really interesting number, E, there's a lot more done with this, and there's a lot more done in like very complex physics and things like that with how E comes about. It's a really cool number to like research.
Okay, so now that we have E, we're going to have functions of the form y equals ae to the rx. This is called the natural base exponential function. So we're assuming that a is greater than 0. When r is also greater than 0, the function has exponential growth. Right? This is 2.7 to the first power, to positive powers.
Well, the first power would be, it would stay the same.
Right, but in exponential decay, this is where a is still greater than 0. So you're still starting with like a positive initial amount. Mm-hmm. And now the r value is negative. So that exponent, r times t, is going to be negative. And so that's really 1 over 2.7, blah, blah, blah. So it's a negative exponent.
Yeah, so you're saying if it's e to the negative something, we'll call it x, that's the same thing as 1 over e to the x, which means this is a decay function.
Right, and because we just learned about exponential growth where the base has to be greater than 1. Mm-hmm. So when the base is e to a positive, the base is e.
Right.
Okay, which is greater than 1 is 2.7. And when the exponent is negative, it's really 1 over e to some power, which is between 0 and 1, yeah, and that's so why it's exponential
1
decay.
1 over e is less than 1.
Mm-hmm.
Right. Okay, so basically you're saying we haven't changed any of the math. Everything we learned before is the same thing. We just have this new special number e you have to think about, which is 2.7.
Right, and the exponent now isn't just x. Exponential growth, it was x or t.
Oh, now it's rx?
Yeah,
so it's like
some kind
number
of rate
x.
Times the amount of, like, whatever the time interval is. So we have the graphs of these kind of parent functions, y equals e to the x and y equals e to the negative x. And they're very similar to exponential growth and decay that we looked at, where the y-intercept of this parent function is 0, 1. The exponential growth looks the same. Exponential decay looks the same as it did in previous lessons. These graphs, these parent functions, also have horizontal asymptotes, being the x-axis or y equals 0. Example 1, graphing natural base functions.
It's a good example 1.
Example 2, graphing natural base functions. Tell whether each function represents exponential growth or exponential decay, then graph the function. In A, the A value is 3. And to know if it's exponential growth or decay, we look at that exponent that e is being raised to, and here e is being raised to the 1x if you wanted, and 1 is positive, so it is exponential growth. Then you would go ahead and put this in your calculator. We wanted to put the table in there so you could make sure you're graphing it right, where x of negative 2 is 0.41, x of negative 1 is 1.1, x of 0 is 3, x of 1 is 8.15.
And you should be able to very quickly get this y-intercept because e to the 0 power, any number to the 0 power, as I'm sure you've learned, is 1, and 1 times 3 is 3. So if I were graphing this, I wouldn't even use the table if I needed a quick sketch. I would just go and plot the y-intercept, which is 0, 3, and then know that every exponential growth function has a shape like this with a horizontal asymptote at y equals 0. So I'm going to go ahead and just roughly sketch this, and we'll see approximately how that matches these values in our table.
And it only has a horizontal asymptote at y equals 0 because we haven't done a vertical translation.
Yeah, there's no plus, I don't know what
plus
letters
or minus k.
K? Oh.
Yeah.
There's no plus k where k is the vertical shift.
Right.
So since that isn't there, our y-intercept, or excuse me, our horizontal asymptote is y equals 0.
Okay. And so looking at B, if you can just pick a different color to do B in, this is an example of exponential decay. The chart is off the screen. Just give the first few values. Because the exponent is negative. It's a negative 0.5, which means if we wanted to make that exponent positive, it'd be 1 over e to whatever power.
Well, to the 0.5.
And then to the x. To the 0.5x. Okay.
Oh, yeah, either way.
So here we have an x value of negative 4, translates to 7.39.
I'm going to do 7.4.
An x value of negative 2, 2.8. An x value of 0.
This one you should be able to get. It's 1.
1. An x value of 2 is 0.37.
So again, I'm just going to plot the y-intercept, 0, 1. This one's an exponential decay. All exponential decay functions look like this. Have a horizontal asymptote at y equals 0.
You don't have to label that horizontal asymptote.
No, you don't need to.
But you do need an arrow at both ends of your graph.
I do need that.
Solving real-life problems. You have learned that the balance of an account earning compound interest is given by this formula, which we learned in lesson 1 before this, number 43. Yes. As the frequency n of compounding approaches positive infinity, the compound interest formula approximates the following formula. Continuously compound interest. When interest is compounded continuously, the amount A in an account after t years is given by the formula A equals PERT.
Which is PE to the RT.
Yeah, where P is the principal, R is the annual interest rate expressed as a decimal. Let's get right to example 3, modeling with mathematics. You and your friend each have accounts that earn annual interest compounded continuously. The balance A in dollars of your account after t years can be modeled by A equals, given a formula. The graph shows the balance of your friend's account over time. Which account has a greater principal? So the principal in our account is the P value, which is $4,500 is our principal, our starting amount. And the principal in our friend's account is the y-intercept, right? At time 0, how much is in their account? $4,000. So we win that one. We have more principal, a greater principal. And now, which has a greater balance after 10 years? Now this is when t equals 10. Color you prepared to do? Great. So we're going to put this formula in our calculator. E to the times 10. And we get approximately 8,713.21.
And 6,713.
Is it 8?
Yeah, you did.
Yeah, okay.
Okay, so here's one thing I should have written. Should have written A of 10.
Okay.
All right, so that's the amount we have after 10 years. This is a function of t.
Now for our friends on the graph, we're going to look at year 10. That's a little above 7,000. So it doesn't ask how much greater the balance is, it just says which has a greater balance.
Yeah, so if this were a Regions question, I would answer the friend's account is above $7,000, so the friend has more principal.
No.
Sorry, not principal. The friend has more after 10 years. Thanks.
A greater balance.
Mm-hmm. The formula to determine continuously compounded interest is A equals PERT, PE to the RT, where A is the amount of money in the account, P is the initial investment, R is the interest rate, and T is the time in years. Which equation could be used to determine the value of an account with an $18,000 initial investment, so that's the P, and an interest rate, let's see, that's the R, of 1.25 for 24 months. All right, so that's the T, except it said they wanted T in years, so we're going to make that 2. So we know that we're using the formula A equals P E to the RT. I think I have this all color-coded. P is 18,000. E is just E. Now the R we need to change to a decimal, so we move the decimal over 2 places to the left, so it's 0.0125. And then the T is 2. Is there an answer choice like that?
Yes.
Which one?
3. Let me point out, this was a Regions problem, so if you're about to ask me, do we need to memorize this PERT formula? Apparently in this example, the Regions spelled it out for you. They're like, this is what P is, here's the formula, here's R.
It's a pretty common formula, and it's an easy one to know. It spells a word, it's PERT, so I would recommend knowing this. It's helpful in biology, in AP Bio, you'll use a formula like this, or if you get to a higher level of AP Calculus, you'll use a formula like this as well.
Great.